Hello guys, good morning. Welcome to Unacademy and welcome to my class. Just let me know whether everything is okay. Am I audible? Am I visible? So if everything is okay, we can start our class. So in today's class, we are going to discuss particle in an infinite and finite potential boxes. Okay, so without any further delay, let's just start our class. My name is Sahin Sorifi and I'm a class educator on Unacademy. Okay. We take this class on every Friday from 9 a.m. to 10 a.m. So 1 hour class every Friday in the morning. And guys, these are our ongoing plus courses on Unacademy. So we are targeting for the upcoming CSIR-NET June 2021. And we are taking this complete course on thermal and statistical physics and detailed course on classical mechanics. These two courses are currently ongoing on Unacademy Plus. And a detailed course on electromagnetic theory. This course is going to come very soon, and mathematical physics course is also upcoming in Unacademy Plus. Now this is our plus class schedule, guys. Thursday, Fridays, Saturday. These 3 days, Thursday 6:30 p.m. to 7:30 p.m. we are taking a class on Unacademy Learning. Every Friday in the morning 9 to 10 a.m. and in the evening also 6:30 to 7:30 we are taking two classes. These are free classes on Unacademy's YouTube channel and Unacademy Learning app. On Saturday 6:30 to 7:30 p.m. we are taking a class on Unacademy Learning app, and Unacademy Plus class we take it from Monday to Saturday from 9 p.m. to 10:30 p.m. Okay, so Unacademy Iconic subscription has been started. You can think of taking Unacademy Iconic subscription as well class subscription using our referral code SahinLive. So in Unacademy Plus subscription, you get daily live classes, you get test series, unlimited practice, structured schedule, and all of these things. In addition to these plus benefits, if you take an Iconic subscription, you will get these additional benefits like personal coach, study planner with bi-weekly sessions, bi-weekly reviews, study booster session, personal doubt clearing sessions, SOP and interview preparation, preparatory study material, and many things. So without any further delay, let us start our class. So what we are going to discuss in today's class. So today's topic basically will be, the title is particle in a finite and infinite potential box. So before we start that, let me just tell you what are the topics which we'll cover. So the first topic which will cover about free particle. Okay, free particle in one dimension. So this is very short thing, free particle in one dimension, because we cannot directly jump to the main thing. We have to start with the beginning. Number 2, we'll go for step potential. Step potential. If you have a particle and it is fed to a step potential, how does it behave? And number 3, we'll go for asymmetric potential box. Asymmetric potential well. Then we will go for symmetric potential well. And after that, finite potential well. So these many things we are going to discuss in today's class. Now without any further delay, let's start with the first one, free particle in one dimension. So we must have read about this free particle in one dimension. So here in this slide, you can see the potential of a free particle. What is the potential of free particle? It is 0. Vx equals to 0 in the range minus infinity plus infinity. So you can directly utilize the Schrodinger wave equation H psi equals to E psi. H is the Hamiltonian operator minus h square by 2m d square by dx square. This is H into psi plus Vx equals to E psi. Now for a free particle, Vx equals to 0. So it becomes del square psi by del x square plus twice me by h square into psi equals to 0. So you can see this equation is of the form like this: d square psi by dx square plus this is k square into psi. This is equals to 0. And you know how to solve this particular equation. You can just you can just find out the characteristic root of this equation. So m square plus k square equals to 0. So you get m equals to plus minus ik. Okay. So these two roots are m1 equals to plus ik, one root, m2 equals to minus ik, this is another root. So we can solve this particular differential equation, and here you see root over twice me by h cut square equals to k, or k square equals to twice me by h cut square. Okay. So what is the solution of this particular differential equation? The solution is given by psi equals to a e to the power ikx plus b e to the power minus ikx, because the roots are m1 equals to plus ik and m2 equals to minus ik. So this is a solution given by given for the free particle in one dimension. And what is the energy? Energy equals to, it can be found out from here, this expression, E equals to h cut square k square by 2m, and it is also written p square by 2, p equals to h cut k. So energy of a free particle is given by h cut square k square by 2. So this energy is not quantized. Okay, so it can take any value from 0 to infinity. Okay, the energy eigenvalue of free particle is E equals to h cut square by k square into 2m. This is continuous. Continuous means it can take any value. And what is the wave function? Wave function is psi plus equals to a to the power ikx, psi minus equals to a to the power minus ikx, where psi plus moves from positive x-axis to negative x-axis, and psi minus moves from negative x-axis to positive x-axis. Okay, so this will be your psi plus, and if it is moving from negative x-axis, it will be your psi. So in this way, the particle, free particle is represented. So I hope this is clear. Free particle means basically we have done v of x equals to 0, potential is 0. Then we put this thing in the Schrodinger equation. We got a differential equation. We solve the differential equation. We got two things. One is psi plus, another one is psi minus. Psi plus is the wave which is coming from positive to negative x-axis, and psi minus is coming from negative to positive. So they are represented by this. And the energy eigenvalue of free particle is given by E equals to h cut square k square divided by 2m. So the free particle is done. Now let's quickly move forward to the next topic, which is step potential. What about the step potential? The potential step is defined as v of x. This is equals to 0, means in this region, let x equals to 0, let's say. So in this region, x less than 0, where the potential is 0, and in the region x greater than 0, in this region, the potential is v naught. Okay, so this is the step potential. Now we are going to consider two cases. So a particle is there, particle is coming, let's say, and this particle will have different energies. Let's say the energy is represented by E. Now two cases are possible. One, the first case is that the energy of the incoming particle is greater than V. Okay, the energy of the incoming particle may be greater than V. And another possibility is that energy of the particle is less than V. So what will be their mechanics if we have the energy greater than V or you have the energy less than V? Okay, so let's consider the first case, E is greater than V. So for x less than 0, okay, if energy is greater than V, sorry, this will be V naught or V, whatever you say. For x less than 0, the Schrodinger equation will be minus h cut square by 2m del square psi by del x square equal to E star. So it will be like same as the free particle, because here also v of x equals to 0. So minus h cut square by 2m d square psi by dx square equals to E psi. So you can write this equation in this form: d square psi by dx square plus twice me by h cut square psi equals to 0. And similarly, the solution of this particular differential equation is given by psi equals to a to the power I k1x plus b to the power minus I k1x, where x is less than 0. K1 is the wave function at this point, K1. K1 equals to root over twice ME divided by H cut square. K1 equals to root over twice ME divided by H cut square. So as usual, A e to the power ik1x, which is moving from the left side, means it is the incoming wave. A e to the power ik1x, A e to the power ik1x, this will be your incoming wave. Okay. And look, there is a step here, so it will get reflected. So a reflected wave will also generate. This reflected wave is B e to the power minus I k1x. K1 will be same because we are considering the same region. It will be going in this way. So this is a reflected wave. Now, some portion of the wave is reflected and another portion of the wave will be transmitted. Okay, so in x greater than 0, we will get the transmitted wave. So in x greater than 0, the Schrodinger wave equation will become, now at this position, v is not equals to 0, v is equals to v naught. Okay, so the Schrodinger equation will become minus h square by 2m d square psi by dx square plus v psi equals to e psi. And that will produce d square psi by dx square plus twice m e minus v divided by h square into psi equals to 0. Means d square psi by dx square plus k2 square psi equals to 0. So the wave function at this position is given by k2, which is equals to root over twice m e minus v naught divided by h square. Okay, and if you solve this particular differential equation, then what will you get? You will get the wave function psi 2. So in the wave function in this region x less than 0 is psi 1, and the wave function in this region x greater than 0 is psi 2. So what is the value of psi 2? Psi 2 is given by how much? C, we have taken A, B, C, A, B, then it will be C e to the power I k2x plus D e to the power minus I k2x. This is in this region x greater than 0. Okay, so in this region, in the first region, we got both incident wave as well as reflected wave. But in region 2, there will be only transmitted wave. There is no chance of getting reflection. Okay, so this C to the power I k2x, this is representing the transmitted wave in region 2. Okay, and D e to the power minus I k2x, this is represented reflected wave in the x greater than 0 region. Okay, but here you see there is no possibility of reflection. The wave can only go through like this. It cannot come back because there is nothing to reflect it. So this D should be equals to 0. Okay, D should be equals to 0 because there are no wave reflection reflected in region 2 and x greater than 2, x greater than 0. So it is quite evident you can see if some wave is coming, so it will hit this potential barrier, potential step, then some reflected wave will be generated. But if we are coming to this region x greater than 0, here you see the wave will only forward in this direction. There is no possibility that it will come back. So this thing is not possible here. So D equals to 0. Now we have got the wave equations. Psi wave function in different region 1 and region 2. Now let's talk about the current density. Okay, so let's say the current density in this region 1 is Ji. Ji is the incident current density. Okay, incident current density, and this current is Jr. Jr is the reflected current density. Reflected current density, and this Jt is the transmission current density. Transmitted current density. Okay, so Ji, Jr and Jt are the incident, reflected, and transmitted current density. Now, how can we define reflection coefficient? This definition is very important. Reflection coefficient. So reflection coefficient will be defined by R. R equals to modulus of this JR and JI. Okay, JR, how much it is being reflected, divided by how much incident current it is. So R equals to JR by JI. And what will be the transmission coefficient? Transmission coefficient means how much percentage of wave is being transmitted. So incident wave is like 100%. Now from the 100%, some portion of the wave is being reflected, so it will be less than 100%, and some of the wave is transmitted, so it will that will also be less than 100%. And accordingly, we define two things. One is reflection coefficient, that will give you the percentage of reflection, and another thing is T, transmission coefficient, that will give you the amount of transmission, JT by JI. Now we know the definition of this current densities. So current density JI, it is given by minus I h cut by 2m. So h cut by twice Im psi incident star del psi I by del x minus psi I into del psi star by del x. Okay, so we got psi 1 in the very beginning. This is psi 1. Psi 1 equals to a to the power I k1x plus b to the power minus I k1x. So if you put that value like here, psi I equals to a e to the power I k1x plus b e to the power minus I k1x. So if you put these values, you will end up getting this value h cut k1 by m mod a square. Okay, and you will get the reflection current density JR is equals to h cut by twice m JR star del psi r by del x minus psi r del psi r star by del x. So this is the formula of current density, and if you put the value of psi r equals to this, you will get minus h cut k1 by m. Okay, so sorry, this will be this, because incident is a to the power I kx. Okay, as I have already told you, one wave a to the power I kx, this is incoming wave, and b to the power minus I kx, this is reflected. So when you are calculating psi I, it will be a to the power I k1x. For psi r, you will put b to the power minus I k1x, and you will get the incident current density and reflected current density as h cut k1 by m a square and minus h cut k1 by m b square. Okay, I hope this is clear. So this is the thing we discussed in case of this E greater than B naught, when we have considered the energy of the incoming particle is greater than the step potential. The step potential height is V naught, so we considered that the particle energy is more than the step potential height. Now similarly, we can find out JT. JT will be how much? JT, transmitted current density, JT will be equals to h cut by twice Im psi t square del psi t by del x minus psi t del psi t star by del x. This will be the JT value, and if you put psi t means transmitted wave function, as I have already told you, what is the psi t? Psi t is this c to the power I k2x, because d coefficient is 0. So psi t equals to basically c to the power I k2x. Psi t equals to c to the power I k2x. And if you put that, you will get the value of JT to be equals to how much? JT will be equals to h cut k2 by m into c square. So kind of similar result you are getting. For JI, we are getting h cut k1 by m a square. For JR, you are getting minus because it is traveling in the negative direction, minus h cut k1 by m b square, and JT we are getting h cut k2 by m c square. And now we can define the reflection coefficient and transmission coefficient. reflection coefficient R equals to JR by JI. This is equals to B square by A square. And transmission coefficient T equals to JT by JI. This is equals to there is a ratio of K2 and K1, K2 by K1, C square by A square. Now we have this situation here like this. This is x equals to 0, this is x is less than 0, this is x is greater than 0, and this height is V naught. Okay, particle was coming like this, it was being reflected like this, and some portion of it was being reflected, transmitted. Now, what is the boundary condition saying? Using boundary condition at x equals to 0. At this position, we are utilizing the boundary condition that wave must be continuous and differentiable at the boundary. Wave function must be continuous and differentiable at this point. What does it mean? It means psi1 means this incident wave function at x equals to 0. This should be equals to psi2 wave function in this region x greater than 2, x greater than 0. This should be equals to at x equals to 0 should be same. Okay, and psi1 you got how much? A to the power I k1x plus b to the power minus I k1x, and psi2 we got c to the power I k2x. So if you put x equals to 0 in both psi1 and psi2, you get a plus b equals to c. So this is the first condition we are getting from the continuity of wave function. Now let's check the differentiability of the wave function at this boundary x equals to 0. Okay, so psi1 d psi1 by dx at x equals to 0, it should be equals to d psi2 by dx at x equals to 0 from the differentiability at the boundary. Okay, if you take the derivative with respect to x and put x equals to 0, you get k1 into a minus b, and that will be k2 into c. Okay, now if you solve these two equations 1 and 2, you will get the value of these two coefficients a and b. You got b equals to k1 minus k2 by k1 plus k2 into a, c equals to 2 k1 by k1 plus k2. So here you see the wave vector at this region is k1 and wave vector at this region is k2. So these values of k1 and k2 we already know. K1 equals to root over twice me divided by h cut square. K2 equals to root over twice me minus b by h cut square. So once you know these values k1 and k2, we can get the value of b and a. And b and a will be utilized to find out the reflection coefficient and transmission coefficient. Reflection coefficient is b square by a square, and b by a we have already got. So reflection coefficient is k1 minus k2 by k1 plus k2 whole square, and transmission coefficient is 4 into k1 k2 by k1 plus k2. Therefore, if you add them up, you get reflection plus transmission equals to 1. So sum of the reflection coefficient and transmission coefficient is 1. And we discussed this case for step potential where the particle is having energy E is greater than V naught. Now let us try to understand the situation where we have E less than V naught. Okay, what will be the situation if we consider E less than V naught? Okay, so the next case is where E less than V naught, means energy of the incident particle is less than the potential height V naught. Then what will be the case? This is x equals to 0, this is the region x greater than 0, this is the region x less than 0. Okay, so firstly we have to consider that when x is less than 0, the Schrodinger equation is h psi equals t psi. The Schrodinger equation will not be changed because here also v of x equals to 0. So minus h cut square by 2m d square by dx square plus 0, this is equals to 0. So you will get the same thing, d square psi by dx square plus k1 square psi equals to 0 as usual. And the solution will be given by a to the power I k1x plus b to the power minus I k1x. Now the question is, if the energy of the particle is less than this barrier or potential height, will it can it be transmitted? Like if its energy is 10 unit and if it is coming with 5 units energy, can it go to this region x greater than 0? So you see, classically this is not possible, but quantum mechanically there is a finite chance or probability to find the particle in this region. This phenomenon is known as tunneling. So classically it is not possible, but the particle can exist in this region x greater than 0 with the phenomena tunneling. So here you can see a to the power I k1x, this is the incoming wave, and e to the power minus I k1x, this is the reflected wave. So particle will come as usual, this will be your a e to the power I k1x, and it will get reflected like this. So this is your psi I, and psi r will be equals to this b to the power minus I k1x. Now this is the reflected. Now what will happen if we consider this region x greater than 0? How does this particle wave will behave in this region x greater than 0? So what we have to do, we have to put the value of v of x equals to v naught, because in this region the potential value is v naught. This is equal to, so minus h cut square by 2m d square psi by dx square plus d naught into psi equals to e psi. This is the Schrodinger equation. Okay, now you can see here we cannot write k2 equals to root over twice m e minus b, because e is less than v naught. So here we have to write 2 m v naught minus e divided by h cut square, because k2 is a wave vector. Wave vector cannot be negative, cannot be imaginary. So that is why we have written, instead of e minus v naught, we have written v naught minus e. V naught minus e is a positive quantity that will not make this k2 imaginary, and as a result of that we are getting a minus sign here. So the solution, the differential equation becomes d square psi by dx square minus k2 square psi equals to 0, and that is giving us the value of the function psi equals to a to the power k2x plus b to the power minus k2x. Why? Because you can do the solution here. You can write the characteristic equation m square minus k2 square, this is equals to 0. Therefore m equals to plus minus k2. So m1 equals to plus k2, okay, m2 equals to minus k2. So these two roots we are getting for this differential equation. Therefore the wave function or solution is written like this: a to the power m1x means k2x plus b to the power minus k2x. Okay. Now you see here in this situation the wave function is given by a to the power k2x plus b to the power minus k2x. Now there is a problem. Okay, there is a problem that if we consider x tends to infinity, then the wave function must vanish. This is the property of wave function, that at x equals to infinity the wave function must vanish. But here you can see this term e to the power k2x. This will not vanish when you take x tends to infinity. So the coefficient a should be equals to 0. Otherwise the wave function will not vanish. That will make this wave function invalid. That is why we have to choose a equals to 0, and we can write psi transmitted. The transmitted wave function is b e to the power minus k2x. So we got three wave functions. First, for reflected, a e to the power I k1x. First one is incident, a to the power I k1x. Second one is reflected, b to the power minus k1x I k1x, and third one is transmitted, b to the power minus I minus k2x. Okay. Now as we have done in the previous case, here also we'll be doing the same thing. finding incident current density, reflected current density, and transmitted current density. Okay. So what will be the value of the incident current density Ji? Ji will be as usual a mod A square into h cut k1 by m. We have already discussed in the previous case. Jr reflected current density. These are not changing. Okay, h cut k2 by m. Now this transmitted current density Jt equals to 0. So you can notice one thing here. Although there is some probability of finding the particle in this region x greater than 0, there is a finite probability. This is given by this d e to the power minus k2x, but the transmitted current density J2 equals to 0. So this is a very noticeable thing. Incident current density will be there, reflected current density will be there, but there will be no transmitted current density. But there is some finite probability to find the particle in this region x greater than 0. This is very interesting. Now, as usual, we'll consider the boundary condition. Wave function must be continuous and differentiable at the boundary. Okay. So we put a psi1 and psi2 at x equals to 0. This would be equals. So a plus b equals to c. This is same. The first condition is same. Next, d psi by dx, d psi1 by dx at x equals to 0. This would be equals to d psi2 by dx at x equals to 0. So a minus b equals to this k2 by ik1 into c, because psi2 equals to d to the power minus k2x. So d or c, whatever you write, you take c e to the power minus k2x. So k2 by ik1 into c. Okay. So we got b equals to k1 minus ik2 by k1 plus ik2 into a, c equals to 2k1 by k1 plus ik2 into a. And from this relation, we can see that reflection coefficient is 1, okay, but transmission coefficient is 0. Jt by ji equals to 0. So there will be no transmission. Okay, but there will be finite probability of finding the particle at x is greater than 0. I hope this is understood. So this step potential is very important concept, guys. You will get a question from this step potential. So we considered here two cases. One is E greater than V naught, and we solve the differential equations, and you got incident current density, reflected current density, transmitted current density. We found reflection coefficient, transmission coefficient, and then we went for the next case, E greater less than V naught. There also we solved the differential equations. We got reflected current density, incident current density, and transmitted current density is 0. Okay, so I hope this is so helping. Now, if you look at the form of the wave function, so in the region 1 means x less than 0, and you see the wave function is oscillatory. Okay, this is oscillatory because psi1 equals to how much? Psi1 equals to, we have got a e to the power I k1x plus b e to the power minus I k1x. Okay, and this can be, if you write the modulus of it, it can be written like this: a square plus b square plus 2ab cos 2k1x. Okay, and this represents an oscillatory wave function. That is why in this region x less than 0, the behavior of the wave function is oscillatory or sinusoidal, you can say. Okay, cos and sine both are known as sinusoidal wave function. Now, when it is reaching this surface and this is boundary, and it is trying to go beyond x equals to 0, means in this region x greater than 0, it is slowly vanishing, because here the wave function is changed. Here the wave function is psi2. Psi2 is equals to c e to the power minus k2. Okay, so here you can see it should give you some exponentially decay function. That is why it is decaying like this. So psi2 mod square equals to c mod square e to the power minus 2k2x. Okay, and that will also give you the probability of finding the particle in this region x greater than 0. Okay, so when E less than V naught, there is finite probability to find the particle at x equals to 0, even if E less than 0, but current density is 0 in region x greater than 0. Here current density is 0. This is a noticeable thing. I hope this portion is clear to everyone. Now let us quickly move forward. So as we have discussed in the very beginning, the today's topic is, the first topic is free particle. So we have covered free particle. Next step potential covered, and the next thing is asymmetric potential well. This is very important. A lot of questions come from this asymmetric potential well. So let's try to analyze the asymmetric potential well. Okay, so particle in one-dimensional box. This is asymmetric because in the right side of 0 we have this potential. It is not there in this way. So that is why this is known as asymmetric potential well. Asymmetric potential well. Okay, so how do we define the potential, this kind of potential? You have a particle in this asymmetric infinite potential well. The potential well is infinite, means the particle cannot escape beyond this. Okay, whatever, how much it tries, it cannot go beyond it, because this is infinite potential well. Okay, asymmetric infinite potential well, and it's defined by v of x equals to 0 when it is remaining in this region 0 to a, and it is infinity otherwise. Okay, now in this type of situation we have to utilize the Schrodinger equation, minus h cut square by 2m d square psi by dx square plus v of x into psi. This is equals to e into psi. Okay, so every time we have to utilize the Schrodinger equation to get the wave function, because in the last class I have told you wave function carries all types of information about some particle. Okay, so our basic target will be to find out wave function. And how we can find out wave function? We can find wave function by solving Schrodinger equation. Now in the Schrodinger equation you can see what is unknown here. Your unknown quantity is v of x, the potential, what kind of potential you are feeding your particle. So here the potential is infinite potential well, which is having value 0 in the range 0 to a, and it is having value infinity otherwise. Okay, so time independent Schrodinger wave equation is given by h psi equals to e psi for region x less than 0 and x for x greater than 0. Okay, so for region x less than 0, in this region the particle cannot exist because this is infinite potential well. So wave function must vanish in this region, and wave function must vanish in this region also at x greater than a. Okay, now what is the Schrodinger wave equation in this region 0 less than x less than a? In this region, what will be the form of the Schrodinger equation? The Schrodinger equation is given by h psi equals to e psi. So h you know, minus h cut square by 2m d square psi by dx square. This is equals to e psi. Okay, because in this region v of x equals to 0. Therefore we can write the Schrodinger equation as d square psi plus twice me by h cut square into psi equals to 0. And if you take the value of k to be twice me root over twice me by h cut square, this equation becomes d square psi by dx square plus k square psi. This is equals to 0. And if you solve this, we get this wave function. The solution of this differential equation give you psi of x equals to a sine kx plus b cos kx. Now once we get the solution, we can utilize the boundary condition at the boundary. So wave function must be continuous and symmetric. Wave function must be continuous at the boundary. So psi at x equals to 0 should be psi at x equals to a, okay, which is equals to 0. Because at the boundary, the wave function must vanish, because here in this region, potential is infinite. So at x equals to 0 and x equals to a, psi equals to 0. Wave function must vanish at the boundary. So psi equals to 0 at equals to psi at x equals to a, this is equals to 0. And if you calculate that, you get the coefficient b equals to 0. So in the solution, we got a sin kx plus b cos kx, and we are finding that b equals to 0. So what we are left with? We are left with the wave function psi of x equals to a sin kx. So this is the wave function of the particle which is lying in this region, 0 less than x less than a. Now further we can put the value of x to, now what is a here? A is a normalization constant. So psi at x equals to a equals to 0. So a sin k equals to 0. So k equals to n pi. N runs from 0, 1 to 3. Okay, a sin k equals to 0 means sin n pi. Okay. So k equals to n pi. So k equals to n pi by a. Now look, n equals to 0 is not possible because that will make the wave function 0. So we'll start from n equals to 1, 2, 3, dot, dot, dot. So therefore, we are getting the wave function psi of x equals to a sin n pi x by a. Okay. Now ka equals to n pi, and we have already seen the wave function value. The wave vector value k equals to root over twice m e by h cut square. Okay. So if you put that value k equals to n pi by a, so k equals to root over twice m e by h cut square equals to n pi by a, and that is giving us the value of energy eigenvalue En equals to n square pi square h cut square by twice m e square. So this is the energy expression of the particle inside a one-dimensional infinite asymmetric potential well, and n can take values 1, 2, 3. So you can see the energy values are discrete depending on the value of n equals to 1, n equals to 2, n equals to 3, n equals to 4. We are getting discrete energy values of the particle, discrete energy values of the particle. So En is the energy eigenvalue which is discrete. Now two things we need to know. One is about the wave function or eigen function, another one is eigenvalue. Two things are there. So we have found out eigenvalue. Now what is the eigen function? Eigen function here, psi n of x equals to a sin kx. So a sin n pi x by a. Now this a is not known. This will come from normalization condition. So what is the normalization condition? Normalization condition is given by this. Normalization condition is given by this: 0 to a mod of psi n of x whole square into dx. This is equals to 1. So if you utilize this, you will get the value of a to be root over 2 by a. Therefore, your wave function becomes psi n of x. This is a normalized wave function, root over 2 by a sin n pi x by a. So this is your normalized wave function. Therefore, you can see the energy eigen function is given by psi n of x equal root over 2 by a sin n pi x. N will run from 1 to 3. N is not equals to 0 because so the value of sin at n equals to 0 will be 0 and wave function will vanish. That is why n is starting from 1 to 3. Okay. Energy eigenvalue En equals to n square pi square h cot square by twice m a square. And orthonormal condition is 0 to a sin star psi m dx equals to delta mn. Okay. Now you can see we got these expressions of psi n of x. Okay. This is equals to root over 2 by a sin n pi x by a. Now, if we choose the different values of n, we get different wave functions. So let's say if you choose n equals to 1, you will get psi 1. Okay. So if you choose n equals to 1, you will get psi 1. Psi 1 is what? Psi 1 of x equals to root over 2 by a sin pi x by a. So this is your ground state. Ground state. We'll try to draw this wave function. We'll try to show you the wave function later on. N equals to 2, you will get psi 2 of x. This is equals to root over 2 by a sin 2 pi x by a. This is your first excited state. If you choose n equals to 3, you get psi 3 of x. That is equals to root over 2 by a sin 3 pi x by a. That will give you the second excited state. So these are basically sinusoidal functions. So we can draw them, we can plot them. So here in this figure, you can see if you plot them, you get this type of wave function. So your energy eigenfunction is sine of x is given by root over 2 by a sine n pi x upon a. Okay. So if you put n equals to 1, that is giving you ground state. So this is the ground state of the particle which is lying in one-dimensional infinite asymmetric potential well. So here you have a particle, it is remaining in asymmetric potential well, and there is infinite. So ground state wave function will be looking like this. Okay. So here how many nodes are there? Nodes means wave function vanishes at that point. So here you see there is no node. So we should not consider this endpoints. We'll consider at this point. So here it is not 0. So node is given by n minus 1. Okay, n minus 1. So if you choose n equals to 1, there is no node. 1 minus 1 is 0. Okay. For this case, n equals to 2. So node is n minus 1 means 2 minus 1 is equals to 1. That is why 1 point is here. For this case, you see n minus 1. So here n equals to 3. 3 minus 1 is 2. 2 nodes. This is one node where the function vanishes. And this is another node. So this is 2. And you can see the plot of this wave function psi 1 over 2i sin pi x by. This is looking like this. This is the first excited state. It is looking like this. Second excited state, it is looking like this. And the energy you can see pi square h cot square twice m square. Then n equals to 2 means it becomes n square equal to 4. N equals to 3, n square equals to 9. Now any function f of x can be expressed in terms of psi n x. N equals to 1 to infinity cn sin x, where cn equals to integration sin star x fx dx. So I hope this will help you to understand this particle in one-dimensional box which is asymmetric. Now let us see a problem. This problem came in CSIR-NET 2012 June. Okay. This problem came in CSIR-NET 2012 June. And let us read the question. A particle of mass m is in cubic box of size a. So we considered one-dimensional box. Here you have been given cubic box. That's not a problem. We'll just generalize. Whatever you have done for 1 dimension, we can generalize for 2 dimension, 3 dimension, whatever it is. The potential inside the box is between 0 to a in x direction, 0 to a in y direction, 0 to a in z direction is 0, and infinite outside. So it's basically we consider this one, okay, and they have just given you like this, means at, so that's like a 3D case. So at these positions, all of them are infinity. So the particle is allowed to move inside a cubical box. Okay. If the particle is in an eigenstate, E equals to 14 pi square h cut square twice m square, its wave function is. So En, okay, your wave function En for 1 dimension we got n square pi square h cut square by twice m a square. Here your wave function will become, for this 3D case, what will it be? Enx, ny, nz, because we are considering 3 dimension, pi square h cut square by twice m a square, cubic box, so length is same, so nx square, ny square plus nz square. This will be the formula. Now this is given to you as 14 pi square h cut square by twice m a square. So can you find out the possible values of nx, ny, and nz? If you find out the possible values of nx, ny, and nz, you can easily tell about this wave function. So what will be the answer? You can let me know the answer in the comment section. क्या होगा answer? What are the possible values of nx, ny, and nz that is producing 14? Tell me your answer in the comment section. What is the answer? Okay, so let's try to solve this problem. So your energy spectrum E, nx, ny, nz. This is for 3-dimensional asymmetric potential will is given by pi square h cut square by twice m a square. Okay, pi square h cut square by twice m a square into nx square plus ny square plus nz square, and it is given in the question as 14 pi square h cut square by twice m a square. So if you just compare these two equations, okay, compare, then what will you get? You can write nx square plus ny square plus nz square equals to the condition. So your wave function will be equals to psi of x, psi, basically psi, not x, because it is in 3 dimension. Psi will be equals to how much? Root over 2 by a. So 2 by a, for x dimension it is 1 by 2, for y 1 by 2, z 1 by 2, it becomes 3 by 2. Sine nx pi x by a, so nx equals to 1, so it becomes pi x by a, into sine ny is 2 pi y by a, into sine nz is 3 pi z by a. Okay, so this is the wave function of the particle in the 3-dimensional cubical box. So option D is the correct option. Let's quickly move forward to the next thing, infinite symmetric potential well. So in the last case we considered that the particle is remaining between 0 to a. Now what we are doing, we are considering now symmetric potential well. Symmetric in the sense it will be symmetric with respect to O. So in the previous case it was 0 to A. So what we are doing is we have just shifted to make it symmetric from 0 to plus A by 2 and 0 to minus A by 2. And the potential is infinity at x equals to plus minus A by 2. So this is the potential V of x. Okay, this is your x. So if you write V of x, this is equals to infinity when x less than minus A by 2 or x greater than A by 2, and it is 0 in between minus A by 2 to plus A by 2. Okay. Now for this symmetric potential box, we'll have two types of wave function. Okay. For this symmetric infinite potential box, we'll get two types of wave function. Now you can see when you choose x less than minus A by 2 in this region. In this region there is infinite potential well. So in this region wave function psi of x must vanish. In this region also it is infinite potential box, infinite potential well. So psi of x equals to 0. So at x less than minus A by 2, your wave function is equals to 0, wave function vanishes. And in this region x greater than A by 2, in this region also your wave function must vanish. Okay. And in this region where the particle is lying, what will be the wave function? It will be as usual A sin kx plus B cos kx. Okay. Now for this case we'll have two types of solutions. Two types of solutions. One for even parity, another for odd parity. So two types of solutions are possible in case of this symmetric infinite potential box. So you can see it in this figure. So psi of minus x equals to psi x means this is for even symmetry. This is the case for even symmetry. And psi of minus x equal to minus psi x, this is the case of odd symmetry. And our wave function psi of x is given by A sin kx plus B cos kx. Now we are going to utilize the even wave function, odd wave function for this case. Okay, so psi of minus x equals to minus A sin kx plus B cos kx equals to A sin kx plus B cos kx. It means A equals to 0 means psi of x equals to B cos kx. Now using the boundary condition, this is x equals to A by 2, this is x equals to minus A by 2, this is x equals to 0. Okay, boundary condition means at x equals to plus minus A by 2, the wave function must vanish, and that is leading us cos k by 2 equals to 0, means k by 2 equals to pi by 2, 3 pi by 2, 5 pi by 2 in this way. That is giving us k equals to n pi by a. So psi n of x equals to bn cos kn by x. This is we are getting by taking even symmetry, means psi of minus x basically equals to psi of x. And if you normalize in the as usual, we get root over 2 by a. So wave function is root over 2 by a cos n pi x by a. Okay. And you can see the value of n equals to 135. So here the values of n will not be 1, 2, 3, 4, 5. It will be taking only odd values 1, 3, 5. Okay. And for this odd symmetry, psi of minus x is equal to minus psi x, we can have a similar calculation, psi of x equals to a sin kx, and from this condition also, boundary condition also, we get k equals to n pi by a, that is producing n equals to 2, 4, 6 dot 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 in this way. And after normalization, you are getting sin of x equal to root over 2 by a sin n pi x by a. So here you see we are getting two types of solution, one for even symmetry, another for odd symmetry. For odd symmetry, we are getting root over 2 by a sin n pi x by a. So here you see n is taking only even values. Okay, so here possible values are 2, 4, 6 dot dot dot. So if you want to summarize the whole thing, then we can say this thing. If you want to summarize the whole thing, we can just write it here that the wave function in case of an infinite asymmetric potential well, symmetric potential, this is equals to root over 2 by a cos n pi x by a when you choose n equals to 1, 3, 5 dot dot dot, and this will be equals to root over 2 by a sin n pi x by a when you choose n equals to 2, 4, 6 dot. So you can notice one thing, that n equals to 1 will be the ground state and n equals to 2 will be the first excited state. So for ground state, wave function will be root over 2 by a cos pi x by a, but the first excited state will become root over 2 by a sin 2 pi x by a. That is why you can see here the first wave function sin x root over 2 by a cos pi x by a. Student gets confused with the symmetric and asymmetric potential. So try to get the difference. Okay, so here this root over 2 by a cos pi x by a, this is the ground state. Ground state having no node. Node equals to n minus, node is given by n minus 1. Node means the number of times the wave function vanishes. Here there is no node because the wave function is not vanishing in between minus a by 2 to plus a by 2. But the first excited state, node equals to 2 minus 1. So 1. So 1 node is there. This is the node. And the wave function is root over 2 by sin 2 pi x by a. Okay, so when you are considering some state which corresponds to odd value of n, we'll consider the cos function. When the wave function is corresponding to some even value of n, we'll consider the sin function. Okay, so don't get confused. And number of nodes here also, this is the second excited state. Here n equals to, let's say, 3 minus 1 means 2. 2 nodes will be there, 1. And look, although the wave function are changing in contrast to the asymmetric potential well, but the energy eigenvalues, this is remaining same, n square pi square h car square divided by twice m square, because we have not changed the width of the potential well A. Width is same. That is why the energy eigenvalue will not change. Only the energy eigenfunction will change, and it will be root over 2 by a cos n pi x for odd values of n, and it will be root over 2 by a cos n sin n pi x by a for even values of n. Okay, so we are running out of time, and I should end the class here. So we have discussed these 3 things today. Okay, so last one could not be covered because of the time. So we covered these 4 things today, and in some other class we'll try to cover this finite potential well. On our YouTube channel also you have this finite potential well on our YouTube channel Physics Hub. You can check it out. There I have uploaded long time back. So guys, you can take Unacademy Pyconic plus subscription, and this is our class schedule. You can note it down. Okay, we take the 3 classes on Thursday, Friday and Saturday, and Monday to Saturday 9 to 10:30 p.m. we are taking plus classes, and the plus classes we are taking this complete course on thermal and statistical physics and detailed course on classical mechanics. So you can attend those classes, and if you want to take Unacademy plus subscription, you can take it using our referral code SahinLive or Physics Hub, and Unacademy will give you 10% discount. So thank you very much guys for joining the session. See you in the next class. Bye bye.